Hello and welcome to our video presentation on the diffserv protocol and networking attacks against it. My name is Russell Waterhouse and I will be covering the introduction and conclusion of this presentation. In this presentation, we will discuss the basics of the diffserv protocol and how it is used to manage network traffic. We will also explore our simulation of networking attacks that target the diffserv protocol and how these attacks can be prevented and mitigated. By the end of this presentation, you will have a better understanding of the diffserv protocol and how to secure it. So first, I will discuss our agenda. We will do a short introduction to the project, the protocol, and the attacks. We will talk about our simulation plan. Then we will talk about the results that we've gotten from our simulations and a little bit of analysis and discussion of those results. So, to introduce the project, our project is to simulate attacks on diffserv to gain an understanding of vulnerabilities and mitigations. Why did we choose this? Quality of service, QoS, network architectures are being used more and more in today's networking environments. This is done to address the resource-intensive networking applications like video streaming and video conferencing. These network architectures are being implemented without a thorough understanding of their threat model. Through this presentation and this project, we aim to develop a wider understanding of this threat model. To introduce the protocol, I'll discuss a little bit about what diffserv is. Diffserv, short for differentiated services, is the most popular quality of service architecture today. It works by assigning a packet priority to each packet in a diffserv header. The diffserv header is shown on the slide on the right. Each router uses this packet priority to determine the per-hop routing behavior for that packet. This allows the network architecture to guarantee a certain quality of service for each packet priority. To implement diffserv in industry, it's a lot of router configuration. I've attached just a few of the router configuration that you would need to tweak in order to implement diffserv in your own network. You can see it on the slide here. So, to move into our simulation plan, we are going to simulate an entire ISP worth of network in a smaller scale in Mininet. You can see the topology that we chose on the right. There are 5 organizations, each with 5 hosts, all connected to a central ISP node. This simulates, as I said before, an entire ISP at a very smaller scale. To simulate network traffic, we wrote custom client and servers to use on the Mininet nodes. Examples of the code as shown here. These are implemented in different ways for different network architectures. My teammates will discuss more about that in a minute. These clients connect to servers at random and maintain TCP connections with them, sending packets back and forth. These clients and servers are distributed through the topology and simulate a full ISP of traffic at a smaller scale that we can run on Mininet VMs.
After we set up the base topologies, the default network conditions is too optimistic for a realistic simulation. Because of that, we have to manually degrade the network conditions. To do so, we use the tool called TC or traffic control. TC is a Linux package that provides a variety of tools which allow us to manipulate many behavioral characteristics of packet transmissions. There are 3 key concepts of TC that we're going to explain in the next few slides. Those are the tools that we use to manipulate the network condition to our desire. There is scheduling, which are achieved by QDisk, classifying, which are filters, and tokens and buckets. Packets are often generated faster than they can be sent. So each network interface has a queue or buffer that saves outgoing packets before they are sent. Queuing discipline, or QDisk, is used to define a custom behavior to choose which packet to be dequeued. The most basic QDisk would be first in, first out, where each packet is treated differently and are sent out as fast as possible in the order they are received. We have 2 main goals when configuring the queuing disciplines. First, we want the traffic not to be sent out as fast as possible by introducing delay, loss, and jitter. This simulates a more realistic network conditions where connections are not optimized. Moreover, in a QoS setting, we want some packets to have priorities over the others. Moreover, in a QoS setting, we want some packets to have higher priorities than the others, so they will be chosen sooner even though they arrived later. To classify which packets belong to which class, we use a classifier or filter. By defining some characteristic of a packet, such as its protocol or payload information, filters can identify which class a packet belongs to, and we will go into more details about filters in future slides. In terms of the actual implementations of the queuing disciplines, they are described as tokens and buckets. Buckets generate tokens that can be given to a packet. Only when a packet is granted a token, then it can leave the bucket. As a result, the rate at which tokens are generated defines the overall rate and behavior of how packets flow through the interface. Moreover, buckets can be chained like a linked list, and each of the bucket can have a different behavior of generating tokens. Here's an overview of the path a packet will take in the system, from the source host to the destination host. Notice how the traffic control only occurs in the egress from the ISP. The packet can travel free without restrictions in any other connections. When setting up our ISP interfaces, we use the HTB queuing discipline. HTB stands for Hierarchical Token Buckets, which is a classical discipline and have configurable transmission rate. This is perfect for our QoS simulations, as different class of packets can have different bandwidths. Looking at the diagram, packets come from the root node. It is then classified by the filter. In our implementation, the classification is determined by its destination or source port number. All packets must go through the max flow node, which defines the total amount of bandwidth available for this interface. After that, the packet can either be in the slow, medium, or fast class. Those three nodes essentially shares the total bandwidth, but with different weights, as bandwidth is more likely to be given to the fast node than the medium or slow node. We do not use these implementations as the tools we use does not seem to be. In the setting file, we limited slow traffic to 300 megabits per second, medium to 750, and fast to 1 gigabyte per second. The result shows a clear difference in the bitrate when connecting through different ports. In a real-life situation, the port could represent different applications or different users.
Alright, so after going over the technologies used in our project and explaining how we set up our network, it was time to start thinking about how we wanted to simulate our attacks. The first step that we needed to consider was how we were going to modify the code such that it simulated each attack precisely. To do this, we altered some logic in the client and server files while also using various parameters to alter the behavior of our network. When running the actual simulations, our plan was to collect data on the network performance and compare it to our regular network. Here is our introduction to the attacks. So, in our attacks, we have a list of all the simulations that we believed to be the most effective on a QoS-based network. The first attack, which is compromising individual nodes, has two different categories. It was theft of services and network denial of service. The second attack, which was modifying a packet header, had only one simulation, which involved just a simple theft of services. The third attack, being quite similar to the first, was with its only difference being that multiple nodes are targeted rather than just one, because it contains theft of services and network denial of service. Our last attack concerns network flooding, whose goal was to send packets to multiple nodes at once with a higher frequency than all other nodes. So here we have a more in-depth description of our first attack, which is to compromise an individual node. In this description, we have two different consequences. The first being a theft of services and the second being a denial of service. To set up the first attack, we would have one node be the victim and another be the attacker. We would then set all traffic coming from the attacker to have a high priority and other node traffics to be a lower priority. For the setup of the second attack, it would be a similar setup to the first, with one node being the victim and another node being the attacker. We would then set the victim node to drop all packets that are not originating from the attacker. For our second attack, we have modification of packet headers, which focuses only on changing the packet headers of the attacker traffic. And the consequences of this one involve just a simple theft of services, and its setup is fairly simple too. We have node B as the attacker, and we'd set the priority of traffic from node B to every other node in the network to be highest priority while not touching the other priorities of other nodes. For our third attack, or third group of attacks, we have compromising a group of nodes, and the consequences of this attack concerns a theft of services and a denial of service. The general setup of the theft of services portion of this attack would have node B as an attacking node, and then we'd set the priority of traffic from node B to every other node to be the highest priority while leaving the other node priorities alone, so somewhat similar to the last attack. Then we have the denial of service, whose general setup would be to have node B as the attacker, and then we'd set all nodes to drop traffic from every other node except node B. For our last attack, we have network flooding, with the consequences of this one being a simple denial of service. And its general setup would just be to have node B as the attacker. We'd set the packet frequency of node B to be higher than all of the other nodes, and we'd also set node B's priority to be higher than all of the other nodes also. Here are our results that we received from our simulations. So for the first attack, which was compromising individual nodes, theft of services, we can clearly see here that one stands out above the others, which, if you haven't seen already, is the brown line here. This is the attacking machine's traffic coming in and out of the victim machine's network. So as we can see here, the brown line has a way more steady amount of bandwidth than any of the others. This is due to the fact that the attacking machine's traffic has a lot more priority given to it than all of the other ones. Like blue here, pink here, cyan here all have low priorities, while the brown line here has a very high priority in comparison. So here's another attack about compromising an individual node with a denial of service. And because of the way we set it up, we set the victim machine's network to drop all packets that were not originating from the attacking machine. And as we can clearly see here, this is the attacking machine's traffic on the victim machine's network. And it can clearly be seen that the brown line is the only color there, aka the victim machine's traffic is the only sort of traffic inside that network because we drop all packets not originating from the attacking machine. And the result of this one is basically that it completely compromises the network. Nobody else can access it but the attacking machine. So for our third attack, we have the modification of packet headers, theft of services. This is the one where we only alter the priority of the attacking node and not touching the others. So in theory, the other nodes could also have a high priority or equal priority to the attacking node, and that can be seen clearly in the picture here. So we have the brown line, which is the attacker. It held up a lot of bandwidth for quite a while there, and then it slowly dropped down, as can be seen here. And as we can see from the picture, it shares the bandwidth fairly evenly with all the other traffics. This is due to them also having a high priority or even medium priority in comparison because they're not all low this time. They're more equal in terms of bandwidth. And the result of this one is that the attack is much less severe than the other DOS attacks we already explored. So here is our fourth attack, which is to compromise a group of nodes, the theft of services portion. So here is the traffic of the attacking machine on two different victim networks. And as can be seen here, the brown line has the most consistent bandwidth in comparison to all the others. This is because the attacking machine has a higher priority in relation to the other ones, which only receive a low priority. It does not completely compromise the network at all, but it does show that the attacking machine steals a lot more bandwidth than it really should have. So here we have compromising a group of nodes, the denial of service portion. And there's not much color, there's not much of anything in this picture, to be honest. Because we set it up so that every node drops traffic from every other node but the attacker, it can be seen here that it's just a straight line of bandwidth, aka the attacker never gets any interruptions or anything along those lines. It will keep sending requests and receiving them just as fast as they request it, basically. This is definitely one of the more severely crippling attack simulations that we ran due to the fact that there's literally no other traffic on the victim machine's network. So for our last attack here, it's arguably the most interesting one. We can see here that it looks a lot different from other graphs, and we can see here that the attacking machine's traffic is clearly given the most priority. It is around 1500 bytes per 10 seconds more than the next runner-up. And this is due to the high priority that was given to the attacking machine's traffic. And we also gave it a higher packet frequency, which allowed us to view this graph here, because all the other ones have a very low bandwidth on the victim machine's network, while the attacking machine has a very high amount of bandwidth. This was definitely one of the more severe attack simulations that we ran.
Now, I will take us through some analysis and discussion about these attacks. So what we've learned. There are massive consequences to these kinds of attacks on networking performance. Even the less severe attacks, like modifying packet headers, can have consequences for the networking performance, and the more severe attacks cripple the network so completely that it is unusable to anyone except the attacker. These attacks should be prevented, detected, and mitigated. Good news is, since we know what these attacks are, we can recommend how to defend against them. This information is based on current industry best practices and the results from our own simulations. So first, defending against compromising individual nodes in a network. To prevent this, you should lock down domain administrator accounts with strong credentials and phishing-resistant two-factor authentication. You should also keep software on nodes up to date. To detect this kind of attack, you should set up workflows that require two-factor validation of changes to node configuration and have active monitoring of these events. To mitigate these kinds of attacks, you should log access to and changes in device configurations. This allows incident responders to find compromised accounts and nodes much easier. To defend against modification of packet headers, you should prevent, detect, and mitigate this attack by, respectively, keeping your implementation of diffserv up to date, ensuring that you are not vulnerable to known attacks. Monitor the ratios of packet priorities. A change in this ratio could indicate that a malicious actor has figured out how to overwrite this packet header and that you might have a problem. You should keep logs of network traffic. That way, when you do detect when hosts or nodes are acting maliciously, you can respond faster to the incident. Lastly, defending against a compromise of a group of nodes. To prevent this, you should lock down domain administrator accounts with strong credentials and phishing-resistant two-factor authentication. You should also have these systems audited by security professionals. You should keep software on your nodes up to date. Remember, if you're using the same version of software on all of your nodes, and that version of software is vulnerable, then there is a vulnerability in all of your nodes. If an attacker figures out how to compromise one node, it is trivial for them to then compromise every other node on your network. To detect this kind of attack, you should set up workflows that require two-factor validation of changes on node configuration. And again, you should have active monitoring of these events. To mitigate this kind of attack, you should log access to and changes in device configurations. Again, this allows incident responders to find compromised accounts and nodes much easier. In conclusion, the diffserv protocol is an important tool for managing network traffic and ensuring that networking resources are used effectively. However, like any other protocol, the diffserv protocol is vulnerable to various types of networking attacks. In order to defend against these attacks and maintain the integrity and security of a network, it is important to understand the types of attacks that target the diffserv protocol. By following the best practices and implementing security measures outlined in this presentation, you can ensure that your network remains secure and resilient against networking attacks.
In the following slides, we will show some concepts that we did not implement due to technical and time constraints. First, we were originally planning to have some sort of traffic control egress from the organization switches. This will simulate a real-life network where there would be more delay, loss, and jitters. We would use two types of queuing disciplines to achieve this. One of them is NightM, which is a simulation tool that includes delay and packet loss, and TBF, which simulate network bursts. To set up the organization switch interfaces, we plan to use network emulators and TBF queue disks to achieve a more realistic network condition. The network emulator will slow down packets uniformly by giving delay and loss. The TPF will burst the packets when going out. We did not use this implementation because the tools does not seem to be compatible with TCP connections. It gave us unpredicted results and cannot be used for our simulation. Nevertheless, our existing implementations still produce meaningful results for the QoS behaviors.
Thank you for watching our video presentation on the diffserv protocol and networking attacks against it. We hope that you have a better understanding of this important topic and that you are able to use this knowledge to protect your network.